What? Yeah. I don't have a saver. Just put it over there. I'll get it. Thank you. Can everybody hear me okay? Can everybody hear me? Hello? Can you hear me? No? Hello? Can you hear me now? Is that better? Okay, thank you. All right, so we're going to look at chapter 3 and chapter 4. And the whole idea of chapter 3 is to get you to the point where you're familiar with the, uh, the basic idea of configuring a PLC. And then chapter 4 is actually doing a program. And I I already went through chapter 3 with you pretty well, but I just wanted to point out to you again that the whole purpose of chapter 3 is to um, introduce you to the idea of how to link to a PLC, and that was about it. So in the case of Siemens, there's 2 or 3 places where you can look at the examples. And this is the Siemens processor. Here it is. And we've taken off the upper and the lower, these covers. In most cases, you will not see these. They're useless. They're okay if you're in the field when you're trying to protect your wires, but here we just take them off and we leave them off. Okay. Now, the idea of uploading and downloading has different meanings in different arenas. If you're a Arduino, you upload to the program in your Arduino. It's exactly the opposite in the PLC. You download to the PLC. So pretend you're in a factory and you're on a mezzanine looking down at a process, and the process is down below you, and you're sitting up in a control room high above the actual process that's going on. And that's the typical example. I shouldn't say never, only 1 or 2 times was I ever up on a mezzanine programming looking down. I was always in a, but by the way, what's the difference between programming here and programming in a factory? What's the difference between programming here and the software is the same. It's exactly the same software. What's the difference between programming here and programming in a factory? You have a running machine here and you have a running machine there. You can have a running machine. You can have a fake machine here, but you can have a PLC that's running. You could be running a process. And there's safety issues, yeah. You have all that. But physically, what is different about it from in a factory? You're probably sitting on a wire spool. You're probably not sitting on a chair. You're sitting on a wire spool. And you say, "What's a wire spool?" Well, it's the only thing that you can sit on that the electricians have kind of discarded, and there's no chairs, so you basically have to find something to sit on in order to program. And you'll be sitting on something that is not very comfortable, but it's utilitarian, and you're not necessarily sitting on a chair. You may be sitting at a table, but that's rare. Most of the time, you've got a wire spool for a programming like a desk. You're lucky if you have a desk, and then you're probably sitting on something that's not very comfortable. Here you've got a comfortable chair and you've got a table. So that's it's kind of subtle, but the differences that's about it, because you're really programming the same kind of program in both cases. It's the same look and feel program, okay? But you're downloading here. You're downloading from, like, on the mezzanine down to the machine on the factory floor. And you're uploading the program from the program controller back into your computer. So you're taking the changed program that you've had working for a while, and you're saving it back now, uploading it back. Okay. Now there's also the idea of saving a program to save the program. That's saving it to your hard drive. So you save a program, you download the program from your computer down to the program controller, you upload from the program controller, and you save it. And those three motions are what you do, basically, okay? But that's this picture right here, upload and download. It's the exact opposite of the Arduino. If you're an Arduino fan, it's just the backwards of it. So you also have this idea of running and programming, and sometimes this rim in the middle. So Siemens does not have a switch. Allen Bradley has a switch. Under the cover, there's a little switch, okay? And Allen Bradley has a switch that goes run, rem, and program, okay? And rem means you can change it in the program, in your software, in your computer. You can actually change it. So with Allen Bradley, leave that little switch in the middle position, REM, the middle position. With Siemens, there is no switch. So basically, with Siemens, what you're doing is you're changing it to run with a statement in the program. It's at the very top. It's on the top line, and it basically has a little arrow that basically allows it to run, and it turns green. And it also both of them turn green on the processor, and then there's a little green in the Allen Bradley upper left. There's a little square that's turquoise or green, and also both of them have what I call goalposts. Allen Bradley has on the left and the right. Siemens only has on the left. But when they turn green, you are running. When they're not green, you might not be running. But with Siemens, you might not be running. With Allen Bradley, you're definitely not running. Okay, but green means you're running, and that's what I look for when somebody's saying, you know, I want to help. You want to help me with this program or whatever. First thing I ask for is, or I look at, is to see, are you running? Are you actually running the program, or is it in the program mode, or is it in the stop mode? Allen Bradley is the program mode. Siemens is in the stop mode. Same thing. You're just not running your program. So you can run the program. You cannot run the program. That's about it. You gotta watch. If it's turquoise with Allen Bradley, it is not running. If it's green with Allen Bradley, it is running. With Siemens, you just look at the light on the program controller. Okay, green always means running. Another thing about Allen Bradley does not have some of the peculiarities that Siemens has, but Siemens has, when you're online and running, you still can't see actively until you click the glasses. So again, there's a separate step with Allen Bradley or with Siemens, which is to click on the glasses to see the green and see things running. Okay, you always have to click on the glasses. Strange thing, but it's, you know, I hate to have to do this, but I hold these up here for a very good reason, because with Siemens, you're not going to see things changing on the screen until you click on the little glasses symbol. Strange but true. Okay, now those are things that I talk about in my videos. So I can't cover all of those things here, but I can tell you that they exist in the videos, and we go through those in detail. The other thing about this is there's 2 or 3 places to look for these videos. With Allen Bradley, I haven't changed since 2021 when I made my original videos. So those videos are found under the hybrid PLC. I'm going to go find those. So I'm going to say I want to look at the Allen Bradley videos. So I type in hybridplc.org. That's my website. By the way, that is my own website. That's not a university website, even though it's blue and gold. It's not their website. The university stopped providing websites to faculty members 4 years ago, 3 years ago. And I had been using the university for my website for years and years. And they stopped. They said, we can't support that anymore. So I went and got one, and I named it hybridplc.org. So anyway, and why the reason hybrid? Because it's both Allen Bradley and Siemens. And I think you get better if you study both of them. Anyway, that's that. Now, this is where these videos are, under videos, believe it or not. And then YouTube channel, and under YouTube channel, there is a playlist. Okay, so the playlist is all this stuff. And down here it says PLC series. Does everybody see that? Okay. PLC series. And under that,
Good
it
morning.
goes by
To start the
chapter.
introduction of the
Okay, it goes by chapter
online
and
course that
it
you're finding in
reflects
these in this
the chapters.
channel, I just wanted to go through and give you some of the options that we presently
I wonder
have,
who the heck is that? That's
and
me.
there will be
All
others.
right, well, let's stop that. Okay, okay, so this is so if you remember COVID, we never knew whether we were going to teach again or not. Live, we never knew. So basically what I did was at the end of COVID, not at the end, but in the middle of COVID, I put everything on video, everything in my book. So I took chapter by chapter by chapter. This was in 2020, so that's 5 years ago now. But I put everything on video. So it's a little dated. The Allen Bradley part is not dated, it's the same, but Siemens, we've moved beyond that. And I'm going to show you where the newer Siemens stuff is. So I'm going to show you, basically, if you look at the Siemens examples in this, if you look under this playlist at the Siemens, it's a little dated. And I did version probably 15 or 16 on this, but anyway, now we're at version 20. And I think we're going to be up and running in the near future totally on version 20. I know, has anybody tried version 20 today on any of the computers here? Anybody have any success? Has anybody tried anything today? Because we're close to getting them loaded and everything up and running, but I haven't. I tried one and it worked, but I haven't. I've been out most of the day, so I can't say for sure. But here's by chapter, and then you can see these, okay? So at the end of chapter 4, there's 2 parts about first Siemens and then Allen Bradley going through this first lab. I'm going to show you this first lab here in a few minutes. But anyway, this is where the old standard stuff is. Now, one of these days I'm going to go through and probably update these videos and update the whole thing. But basically, I've gone through, you can maybe understand, maybe not understand, but as new things happen each year, I go through and I update my book because I don't have to, because it's not a published book. It used to be published, it's not published anymore. I don't have to go back and get it republished or whatever, so I just update it on the web. I have not updated all the videos, but the Allen Bradley part of this is good. I mean, it's still the way, everything is rock solid on Allen Bradley. What's not rock solid is the Siemens part, and I'm going to show you where the newer stuff with Siemens is. It's under the Rubik's project. So again, here's my playlist for the Rubik's project, okay? So here is the same lab that's in your chapter 4, is that right there for Siemens version 20. All right, so when we get the Siemens ready to go, and it's within a day or two of being ready to go, that will take you all the way through that lab, everything. Okay, it'll lead you all the way through it. And some of these later ones, traffic intersection, same thing. And the cash register, the same thing. Those are chapter 7 labs, but they're there. They lead you the whole way through, okay? And then week 4 and week 5 are the same thing with wired, those two. So I go week 2 and week 3, I do the traffic intersection and the cash register. Then week 4 and week 5, I do the traffic intersection and the cash register. Week 4 and week 5, I do the hot dog and the traffic intersection wired. So if you want to know the difference between using the HMI for everything and using the wired, week 4 and week 5, take week 1 and week 2 and show you wired versions of those. So if you want to look at those and see how they are wired and how to do them with wired, there they are, okay? That makes sense? Week 6 is the last one that I do prior to jumping off into the Rubik's project, and it is week 6 is the Simon Says program, which is one of the programs in chapter 13. And you wonder why I'm telling you that, because it's a free swing at a rather complicated lab, but it's totally done. It's totally, I did it in a video, I gave you the program. Now, at the end of chapter 13, I ask you to write the program for it. But here, I actually give you the program, and you can just look at it and type it in and get it to work. It's a good lab. It's a lot of work with matrices, and it's the old game Simon Says. Okay, if your parents or grandparents had this game that you could, it's a memory game. You actually program it. I actually did it here. And the reason that we do this program is it shows how to index through a matrix. It's the exact same thing that you would have done indexing through a matrix, okay? And I don't use random programming. I just say that you're playing the same game every time. In other words, you're playing the same 15 or 20 memory positions every time. You're playing the same game. We just go through the matrix again. It's not a random number generator program. It's just but anyway, then I go into a explanation of a stepper motor, which is chapter 17. And that's a 4-point lab. So if you want to know how to do a stepper motor to make it turn, there it is. That's chapter 17. So these labs, which are these extra labs that I've done just recently for the high school students, you can pick off and have any of these you want, because they're yours as well as theirs. I don't really care. And then we go into their actual Rubik's Cube project. And one of these nights, I'll step back. I'll just give you a little bit of time to go through the Rubik's Cube project. And I'm not ready to do that yet, but I want you to know that if you are interested in doing that, and several people have expressed an interest in doing that, I'll give you like half of your points for your 40 points. I'll give you 20 points if you can get the white cross, okay? It's a bear of a project. It's not a simple project at all. It will show a lot of competency. So if you're kind of interested in that project, I'll give you the 20 points. And if you go further, the points will be negotiable after that. But that's the point that I will say I'll do that much. If you can get to the white cross. Now, what do I mean by the white cross? I mean, you take the Rubik's Cube and you turn the power on, and I get to mess it up. Okay, I mess it up. I can do anything I want. In other words, randomize it. And then you look, then we turn the power on. And you look on the screen and you put the colors, the tiles, you enter on the screen the way that the tiles are at present. And then you hit a button and it does this, and it gets the white cross on the top automatically with the machine. You say, that isn't hard. It is. And I know it is because it is hard to do that. It's a programming project that is relatively very difficult to do, but it can be done. And in the book that I have, this is a separate book. This is the book for the high school students. In the last part of that book, I actually show you how to program it. Even though I don't give you the program, I show you a method, which is a chapter 13. I use matrices for this. So again, I show you how to step through matrices a little bit. I don't give you but if you look at the Simon Says program and you get in your head how to step through a matrix, and then you look at this project, it's the same thing. It's not exactly the same thing, but it's close. So again, I'm telling you that because I want to explain all this stuff to you, because I got two things going on right now in PLC land. I got these high school students, about 300 high school students, over 300 high school students doing this project out there in high school land. And I've got a bunch of teachers and stuff like that doing it as well. And then I've got you. And I'm not saying who's better or who's got more time or whatever. They got a lot of time. There's TTA, Tutor Technology Academy. There's 4 students there, 3 or 4 students that have 3.5 hours, 5 days a week. They're working on nothing but this from now till the end of school. So I guarantee you that they're going to get a good amount of it done. And they're good programmers already. But I'm telling you that it's a good project. And I had a master's student, he's not here, I can speak about him. he basically told me that he was a master's in mechanical engineering, and he basically told me that his work the last 2 semesters on that rig and scoop project made him into what he feels is a competent controls engineer, and I believe it, because he learned so many things about writing programs, troubleshooting, and being able to program, but he feels very comfortable in being able to advertise himself as a controls engineer. So that's the net of that project. It's not trivial. It's very complicated, but it does have a really good. Anyway, that's that. So basically, I'm telling you that wait a day or so, and we'll have the Siemens all up and running. I think they're up and running now, but I'm not absolutely sure. But you can do that. We'll confirm it this week. Okay, that we'll get them all up and running. Okay, so that gets you a little bit of this, what we're trying to accomplish. Okay, so this is chapter 3, and we talked about upload and downloads. Very important concept, uploading and downloading. And this is this old control panel. Let's get back and talk about chapter 4. Chapter 4 is right here. I don't want to do that. Okay, so now again, what you cannot do that you could do in a wired circuit is you cannot go backwards. You can only go left to right, up to down, and down to up. So you go down, you go back up. You cannot go right to left in your circuit that you may design. And now you can program this on the computer. You can actually set this up, and it looks like it might work, but it will not. The algorithm will not process moving from right to left. It will not do it. Okay? Now, these are pictures of the programming area of the various machines. And this is the Siemens one. This is the area that you're going to see, okay? Now you're going to see on the left the project tree. You're going to see the PLC program. You're going to see the HMI program. Over here, you're going to see the instruction list, and that's about it. Up here are the various things you can do, and up here is where you can do the compile, you can do the download, you can do the start of the if you're online, you can do the start of the PLC. You can start it up. You can make it go into the run mode. You can stop it. You can do all that kind of stuff. When you're online, up in here is where the glasses are. So that's kind of and it goes through and tells you these various areas and that type of thing. So this is, in the middle is where the sheet is where you can start programming yourself. Now, one of the things about Siemens that is interesting is this area right in here is divided into networks, okay? Now, there's a line, there's an area up there, then there's a line, there's another area, there's another line, there's another area, okay? Those are called networks. The network term came from Modicon. So Siemens borrowed from Modicon this term of network, all right? But then within each network, you can program multiple rungs, okay? Now, what is the advantage of putting all your program in one network? It crunches it together, and you can see more on the screen at one time. I'll be blunt. Yes, sir. It is. Okay, so a network kind of is as big as you want it. okay? But the solving of the logic within a network sometimes gets odd. And one of the first things I want to tell you is, if you go from top to bottom, if you're trying to work your way down through a program, and something up here sets a bit that then is used later on, and you put it on the same network, sometimes it does not work. So my solution to that is to tell you, oh, it isn't working. You say, oh, it isn't working. And why isn't it working? You see it working, you think it should be working, and it's not. My solution to that is to split it up into multiple networks. Okay? Why it doesn't work, I don't know, but it sometimes doesn't. So, you know, it's like when you have a headache, you take an aspirin. If somebody asks me, it doesn't work, what's my first explanation? I don't know, split it up into multiple networks and see if it works. Okay? So you can put as much as you want to into a network as long as it works. The minute that something stops working, then you split it up and make it into multiple networks. I don't know why sometimes it doesn't work. It just doesn't. Because things that are set over here, should affect the next rung down, the next part of that. Most of the time it does. Every once in a while it doesn't. And I can't tell you every instance, I cannot express to you every instance about why it doesn't do that. With Allen Bradley, it is truly rung by rung by rung, okay? Allen Bradley is like a scroll. It's like you're reading an old, papyrus scroll, and you're scrolling through these rungs. And this rung sets something, and then it's used in the next rung. And that sets something, it's used in the next rung. And that sets something, it's used in the next rung. It's a sequential operation. But this sets this, this sets this, this sets this, and it goes by rung. This does not necessarily do the same. It kind of does, but it doesn't do it all the time. Okay? So if you wanted to be safe, you would say every rung, every piece of logic with a call at the right would be a network. And that's okay. But then what happens? You don't see very much at one time. So you start putting more, and you look at my programs. I put a lot of stuff in each rung, or in each network. On each page, in other words, a network is like a page. Okay? A network is like a page. And you'll see that. I'll start, and then I'll make another little, what I call a sprig or a little jumper down, and then I'll do another one. You look at my program and say, why is he doing that? Because it works. And you can see more on the screen at one time. Why is that important? You're troubleshooting, and you don't have to keep scrolling up and down. Okay? Another thing that is very important is you judiciously use names. Okay? Now you only have so much room on the screen. And some people like to write the Encyclopedia Britannica as a name. Okay? And I've had people that have made me do that. And I am very much against that. I like short names. I do not like abbreviations. I like short names. But you can do whatever you want to do. But if you make a long name, that spreads it out so that then you don't get very much logic on a page. And it keeps wrapping around, and it keeps going down. And that's not what you want. So you basically want to have names that are short, but that are meaningful. So how many characters can you have in a name? I think it's like 64. You can write a book on a name, okay? And these names are stored down in the program controller. So everything is stored in the program controller. The older program controllers did not store the names in the program controller. These do. Both of these do that same thing. And this changed about 25 years ago. Why? A little story, okay? So I don't, nobody asked me why, but in the old days, they had names for things like B13 or whatever, okay? That would be a name. Now, the associated name with that B13 would be stored in the program control, and not in the program controller, but in the computer. But if you were to read B13, you would have no idea what that was, okay? But the name would be stored back in the computer. Here's where the rub is. There was a lot of turbulence in the day, and I don't think there's as much today. I think there's more loyalty to the employee than there ever was, because they want you. They want to keep you happy. They want to keep you happy in your job, and they want you to do this work because they don't have enough people doing this. But in the old days, there was a lot of layoffs. Okay, layoff came and went, and people would be out. So maybe a person would be the only person that would have that file of those names for that project, okay? And he would keep those tight to his self. So if you ever fired him, and when he walked out, the day that he walked out, all your nomenclature, all your identification of what things meant, all your identity would go with him. So basically, they made it so that everything went to the program controller, including all these names. So a name of a bit now, or name of a coil, is put into the program controller. Memory's cheap, and the names all go down to the program controller. So if the guy got fired, and you wanted to, a month later, go back and retrieve that program out of the program controller, all the names would come with it. Didn't used to be that way, but that's the way it is today. Okay, so the names are important, what you call things are important, and they're all stored in the program controller. Up until about 20 years ago, that was not the case. And with Alan Bradley, the RS Logic 5, the RS Logic 500 programming style and RS Logic 5 programming style, that was the case. The old Alan Bradley style, and I'll go through that in chapter 5, because I kept that. You'll look at this book and you'll say, now, why did he do this? And sometime I'm going to probably get rid of it, but up until a few years ago, the argument was because it's still out there and people are still using it. I want you to understand what that architecture is, the naming architecture for the older style Alan Bradley. But today I'm not quite as sure, but I still have it in there. We'll go through it really quickly. But anyway, that gives you a little bit of the flavor of the work area between Alan Bradley and Siemens, okay? Now, what do you call things? Here, it is important that you get this idea that Alan Bradley, every named thing in Alan Bradley is not, there are no physical locations you can go to and look and find those, where those words are, okay? So in other words, if you give something a name, a bit, let's say a contactor off of something, okay? So in Alan Bradley, if you were to program that and call it something, let's call it X1, okay? X1 is stored somewhere, but you don't know where, and you don't really care. You give it a type called bool, and you're done. Basically, that's it. All right, this is Alan Bradley. Now with Siemens, you can call it X1, but you also have to give it an M-bit address. This is Siemens. So Siemens has this extra table called the M table in OB1. In their main program, OB1, Object Block 1, they have this M table that goes along, okay? Now, why did they do that when Alan Bradley went to this approach? I don't know, but when they restructured about 20 years ago, 25 years ago, Alan Bradley totally got away from having a fixed table. There's no fixed tables with Alan Bradley, the newer style. It's all just hidden. Siemens kept this M table, I think, because they had to have a link to old systems. I don't know why, but I think that's my object perception, but I'm not sure why they did. But now, why is this important? Well, and then And then Siemens also allows you, and both of them allow you to go off into another area and basically program other than OB1, and you can program exactly like Siemens, or exactly like Allen Bradley, where there are no M table addresses. So you can have, I know this may be confusing to you, but you can have, in Siemens, you can have this OB1, but you can have another object block that looks like, exactly like AB. Okay? But most of my work is in OB1, so I'm tying you to this M table for most of the stuff that I do. Okay? As I get smarter and I write more and I do more, I would think that you probably will think about this and you say, well, if I really want to write a bigger program, I'm going to write it in something other than OB1 because I don't like the idea of having to tie it to an M table. Why is that important? Okay, I've got a deck of cards. All right? Now I can use each of these cards for a specific thing. I can use this card for that bit. I can use this card for that bit. I can use this card for that bit and this card. But what happens after a while? I forget what each of these cards meant and whatever I did, right? And I erase the one, but I forget the fact that I may have used it for something else. Okay? Now, if you double use a bit, it does not tell you. So I can have a coil that's using a bit of M-bit territory for one thing, and then I can have a coil someplace else that's using that same bit for something else. Now, who wins? Last guy wins. Because as your program executes down through it, you've got this, and you 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 got this. The last time you use that bit with that name is the one that wins. So if you double use a bit using the same M-bit reference, it joyously doesn't do the first one, but will do the second one. So if another thing that might happen is you say, I'm looking at this coil, this rung of logic, and it's green all the way across, but the bit that is the output bit is off. You know what the first thing I'm going to tell you is? You double use that bit. And about 90% of the time I'm right. I've been through this war enough. And one of the first things you're going to do is you're going to forget and you're going to double use a bit. Okay? It's natural. It's the thing that not everybody, but some of you will do. You will double use a bit. It's like playing of cards. You will use that card more than once and you'll forget about it. Okay? Or you'll use that word, that 16-bit word, as a word as a number, and then you'll use bits in that word as coils. Again, can't do that, but you can do that. They'll let you. Buyer beware. Now, when you're first programming, it peels off those bits one by one. You'll see that once they use it, you can't use it again, can't use it again, can't use it, but you can go back and use it. Oh, yes, you can. So this M table is a double-edged sword, and it's something that you can use, and you have to get used to using it because it's where you store your words and your bits in OB1. And we do most of our programming in this course in OB1. Why is that the case? It's the most simple place to program, OB1. Okay? It's your main program area. But once you get outside of OB1 and to one of the other OB's object blocks, you have this problem. And most big boys, most programmers get out of OB1. Okay, and they program elsewhere. They program in another object block. They don't program in OB1. They get out and they do it elsewhere. And the programs, the nice thing about that is the programming that you look at in Siemens and the programming you look at in Allen Bradley, from that point of view, almost looks identical. It's exactly the same look, feel. You can make them look exactly the same, almost identical. Okay? It looks 99, not 99%, but about 90% the exact same, and they work almost identically as well. All right. So now that's a real quick overview of the M table. But the good and the bad about the M table is that as you're working through programs, I show you how to attach a bit in Siemens to an M bit. So you look at the video and I show you exactly how it's done. The other thing about the M bits is they're global bits, okay? The M bit goes all the way across every program in the whole thing. It's a global. Do not use the default, which is the immediate bit, okay? Now, why not? Well, the immediate bit in the program is a bit that it is lost at the end of the scan. So you go through the scan one time and it's gone. If it was on, it's turned off at the end of the scan. So it's wiped clean at the end of the scan, and you start through it again, and it does it now. Now, why would we ever use those things? Well, to pass data into the program, you can pass data or bits from here to here, okay, but if you have to remember it and it has to come back again, it's gone, okay? And if you wonder what my analogy there is 51st dates. Drew Barrymore, every day she wakes up, she's, who am I, where am I, what am I doing today, all that stuff. That's an immediate bit. You do not want those. They're the default. When you're programming Siemens, it comes up as a default and you're going to hit on it and you're going to put a few of those in and you're going to say, now how do I get rid of these? I'll show you, not right now, but I'll show you how to get rid of them. But you do not want to use immediates. You want to use global bits for names, okay? Look at my videos. They go through this in infinite detail, and the best ones are the ones down in the Rubik's project, okay? I go through that because for high school students, there's a lot of detail, a lot of detail in those videos, how to do that. Any questions so far? I know I'm going through this very fast, but again, I want you to understand that, so here is talking about, in Siemens land, how to program and give names and that type of thing. And that kind of gets through that a little bit. Now we get down here to the end of this, and we actually then talk about a lab, which is the hot dog lab. And this is how to do programming, that type of thing. Here's your M bits. They show up right above it. And it's it's byte.bit. So this would be byte 0, bit 0, and it'd be 0 through 7, and you go to the next byte, that type of thing. I is an input from the screw terminals coming in. Q is a output to a screw terminal output. M, these are internal bits. Okay, and this is Allen Bradley. Now, Allen Bradley does not have as much going on the screen as Siemens does, but you can get this as far as with Allen Bradley as you can with Siemens. I'm serious. They're very competitive as far as I'm concerned. They're 6 1/2 dozen others as far as the look and feel of their screen. Some people like the Siemens approach. Some people like the Allen Bradley approach. I personally will tell you something that you may not believe, but I could program faster in DOS than I program in Windows, because you learn the commands on the keyboard, and you could go very, very, very quickly through the commands in the DOS mode. And I don't think they brought those over very much at all, but I was able to get programming done much quicker in the old DOS format than in the Windows format. But we're stuck with Windows and we'll live with it. But again, I want you to understand that they both have the look and feel of the project tree on the left, and this area over here is the programming area. They do have a little bit of differences. Allen Bradley does not have as many instructions, but they can do the same thing. okay? There's not a lot of difference between the two. The competitiveness comes and I'll be blunt, Siemens does have some advantages. The one is safety, the big one is safety, and the other one they've always touted as function blocks. But Allen Bradley now is function blocks, so you can build a function either in Allen Bradley or Siemens. Because the functions came along since I did most of my work in Allen Bradley, my function block chapter, which is chapter 14, is specific to Siemens, not Allen Bradley. And one of these days I'm going to have to go back and put the Allen Bradley in there, but I just haven't done it yet. But they do have function blocks. Okay. I don't feel like I'm doing this justice, but again, you're going to listen to the videos and get much more from the videos than you do from me talking through it. But I have to talk through it just to kind of, as they say, check the box just a little bit. I want you to understand that you're going to, okay, one of the biggest differences with Allen Bradley and Siemens is the tying of a parallel loop, okay? So Allen Bradley does not, it's like throwing a rope, okay? So they throw a rope, you click on that little guy right there, and if your cursor is right here, it does this, and then you drag this to where you want it to be. Okay, so you drag it, and then you put the cursor back at that point to tie in the contact. So you throw the rope, and then you go back and put in the contact. Siemens, well, it's done point by point by point with Siemens. A little bit more. With Allen Bradley, you have to physically throw this rope. You throw the rope around the contacts that you want it to round, and then come back, bring your cursor back here, and then type in the one you want. So with Allen Bradley, it's like throwing a rope around it. And you have to bring the cursor back. A little different than Siemens. That's one thing that is definitely different, okay? And when you're online, you have to go through all these steps, okay? Edit rung, verify rung, and then test the rung. And then finally, if you're in the online mode, then you get to do then you run it. At the end of the test, you get to run it. Stay away unless you are pretty good at it, doing many online changes with Allen Bradley. You'll see, with Allen Bradley, you'll see online, if you make a mistake, you'll see green, and then you'll see a bunch of E's and gray. And if you see that on your online program in Allen Bradley, it means that you've not verified this area and this part of it is not running. It's running up here where there's green, but right here, this part of it is not running. Okay? And you have to go back and you have to verify it and test it. So you got to right click on this, right in here, right click on this area, then verify, then test, then set to run, and it'll take off and run. But you have to do about 3 steps in order to get this part of it fixed, if you see that in your mode in the Allen Bradley. Okay, Allen Bradley has a main program, and then most of the time you branch off to subroutines to do most of your programming. In here, we just basically write everything in the main program. We don't get big enough programs that we have to branch off to subroutines. But every program that I've ever written for Allen Bradley, you have a main, and then it branches to subroutines, and then you just write subroutines. So everything is done in Allen Bradley usually is done in subroutines. So that's the way it's been done in the past. Now with functions, they can maybe do functions as well as anybody. But anyway, we talk about functions later. We can't talk about everything all at the same time. So they have types. And then this is the other thing about tying to I/O with Allen Bradley. It's a little different, and it's explained in the video, but tying to a data block or a I/O block is using an alias. So you're aliasing a name of a bit to a bit in the IO table. So you're aliasing, and you have to do that if you're tying to an IO, an input or an output. You have to alias. Again, in the videos, but you can see it here, and it's one of the harder things that I have to explain because it seems like there's about 3 or 4 ways to do it, and I can mess it up with the best of them. But aliasing is the basic way that you tie IO to a bit in your program. Right here is an aliased bit. It's called input 0, but it's aliased to this hardware bit. And these are the jumpers for the Allen Bradley. If you don't have these jumpers in here, your outputs aren't going to work. So you bring your hot wire, your 24 volts into here, and 1 and 4, you bring your neutral or your 0 volts into 2 and 5, and they're in this jumper. If you don't have that jumper in there, your outputs don't work. Okay, troubleshooting just a little bit. This is the going online for Allen Bradley or for Siemens, the little orange thing there. And you compile it, and then you go online. And here's the glasses. Here's the infamous glasses, all right? And they show up in more than one spot. They show up in the running program. They also show up in the watch table. One of the other things that differences between Allen Bradley and Siemens, Allen Bradley did not have watch tables for a long time. Now guess what their latest thing for Allen Bradley is? They have watch tables. Why? Because Siemens has had watch tables for quite a few years. So basically, you know, it's the competitiveness between the two. But what is a watch table? Well, it's like a data table where you can watch things, and you can have multiple watch tables, and you can detach them, and you can have them all over your screen, so you can be watching stuff over here, stuff over here, and stuff over here, and stuff over here. So you can have multiple watch tables, you can build them and save them, and you can be watching things as they occur. And you can also change things from watch tables. You can enter data and make changes to the data through a watch table. So again, I don't think version 32 of the Allen Bradley software supports supports watch tables. I think you still have to, in Allen Bradley, have to just use the data table, and it's just one data table. But the newer versions, I think, do have watch tables. So again, you say, well, Allen Bradley's better than Siemens. No, it's not necessarily true. They both do the same basic stuff. They both can do the same basic stuff. There's your glasses, and here's the goalpost. See, with Siemens, it's just the left goalpost. With Allen Bradley, it's the left and the right goalpost. If they're green, you're online and running. And that's what I look for. I look for the orange, the Siemens, and then I look for the green goalposts. With Allen Bradley, I look for the green right there. It says run mode. Green is run. Turquoise is program mode. It isn't running. So if it's green, it's running. If it's not, that's what I look for. And eventually, there's my double goalpost. There's the left and the right goalpost. Now that program is online and running. You're looking at an online program that is running with Allen Bradley. See the left and the right goalposts? Okay, getting there. Slow but sure, right? The hot dog counter. This is your first program that you actually enter in using the magic of the PLC. Okay, now, what is this? This is a real-life project, and this actually, somebody wrote one time, enough on hot dog counters. You know, we do more important things than talking about food. This wasn't about food. This was about a real project that actually happened. And it actually, then I brought it into teaching because it's a good program. It's a good little bitty program. And I gave it to the first group that I had, and one person came up with a solution, and daggone it, that's a very good solution to that program. Now, it wasn't hot dogs. What was it? Well, it was a foundry, okay? And not to say that anybody was cheating, but there was a discrepancy between the parts that the foundry say that they were making and the actual parts that were being handed over to the next, to the machine shop. Okay, there was a discrepancy. And we don't know whether anybody was cheating or not, but we'd like to know if they're actually the same. So I looked at it and I said, one guy pushes the sand, which is the basic thing for sand, for making a poured part, and they would get a big pot of sand, okay, a lot of sand, and it would go into the cope, COPE, right? And the other part would be the drag. So the two parts would then be made together, and then what would happen was the cope would be turned over, cope's on top, drag's on the bottom, and then they would come along and they would pour the metal. It was bronze or brass, it was brass foundry. They would pour the brass into the mold, and then they would have the part, okay? Now, what was my observation? You pushed a button, you got sand, you got a lot of sand, okay? So, what was my observation? If you push the button, that meant that you actually made a cope or a drag. And you can make them in any order. You can make the cope first, the drag, either one. That makes sense? But when you make a cope and a drag, you got a part. All right? And guess what? Once I put that in there, the numbers matched up. No problem. And it actually worked. So it actually doesn't matter. I do not like ever advertising, doing anything for Big Brother. I was not a Big Brother programmer, and I did not like writing things that would report on people. And that was one of the few times that I ever did. I'm not proud of it, but daggone, it's a nice little program anyway. So this is not to say that I did this on a regular basis. I didn't, and I don't like doing it, but I did it once, okay? So anyway, so here's where you push the button. You push the button and it says, okay, now I remembered that you got ketchup. Here's where you say, I remember that I got mustard. Now here is a line that's very interesting, because if you push the button and then it remembered it, it says this bit or this bit, right? And when you do both of them, it should turn this bit on, except for the fact that your finger's still on the second button. So these two say, does everybody see that? Now, if you didn't have these two bits in there, what would happen? The second one that was on, it would turn this on, turn that off, but then your finger's still on the button. So as soon as that happened, it's about 10 milliseconds, it'll seal that second one in. If you don't have these two in there, it'll seal that bit up there back in, and all you got to do is go ketchup, mustard, ketchup, and every time you do another one, it'll count up again, and you don't want to count until they're both done. That makes sense? If you alternate, if you don't have those two concepts in there, if you just alternate, you're going to count every time you push either button, which is not what you want. So again, this is subtle, but it's what? Real world. Everybody follow that? This is not something that I would expect you to roll right out and program and get, but I'm giving it to you. But I want you to understand that this is not just easy program number one. It's not. It is easy to type in and it's easy to get an answer, but the subtleness is real. There's something going on here that until you try it and we'll take those two bits out and see what it does, it messes up. If you push the alternate buttons, which you could do, and get a count every time you had either one or the other. Okay? Enough on that. I thought about changing it back to cope and drag, and I thought, no, it's not worth it. Ketchup and mustard you can picture, but cope and drag is really what it was. So this is a real project. It really happened. And I didn't program it this way. I was more sophisticated. I had all kinds of stuff in there. But this is good enough, and it works. Okay? Is this the only time you ever remember having two asymmetric, or what you call, not asymmetric, but asynchronous events tied together? No, there's a lot of asynchronous events in the real world that you have to tie together, okay? The cow project that I think I told you, did I tell you about working on a cow project? Did I ever tell you about that? Don't remember telling you that story? Did I tell you about one summer a rendering of working in a slaughterhouse, a big rendering plant? Did I tell you about that? Okay, I did. Anyways, good money. I would have never done it except for it was interesting. But anyway, so what was an event there that you had to do, take dissimilar things and put them together? How did the rancher get paid? An ear tag with a 20-digit number on it was read into an RFID tag reader, and then the animal went over a live weight scale. And those two things had to be tied together. They had to physically be meshed together so that you had what we would call a packet of information that went forward. That here's the 20-digit RFID tag, and there's the weight, okay? And they had to go forward into the business system carried together. Now that's a trick, because if it doesn't work, what happens? You get paid for the wrong cow, right? If you don't do it right, it gets wrong. Anyway, there are a lot of things where you have to bring dissimilar things together and then move them together as data and all that kind of stuff. So this is not the only time that happened, but it's interesting. So there's how that's done. And then this is a counter, and I show you how to do it in the videos. I show you exactly how to do it. But a counter is something we're going to study in chapter 7. So you have to wait a little bit to do chapter 7. Any questions so far? Okay. Just an intro to chapter 5, and then we're going to stop. Okay, so chapter 5. So in teaching digital logic to the electronic technology students, we used to have two quarters of one is called combo, one is called sequential. Okay, combinational logic and sequential. Right? Combinational logic was and or, like we just did on this quiz. Okay, that's combinational logic. Then what's sequential logic? It's memory, setting of memory. So you have a JK flip flop or an set reset flip flop that would set a memory that you actually did. You go step by step by step through a sequence. Okay. Now think about a sequence for a second and think about what would entail a sequence. Okay? On your garage door, when you key in your number, it has to go in a sequence, right? It has to go 1, 2, 3, 4 times, and then doors open, door closed, right? That's a sequential operation. Combinational logic is a straight and or logic. And if this, then that, if this, then that. There is no memory associated with it. So chapter 5 is just looking at combinational circuits, ands and or circuits, and that's all we do in chapter 5. Okay. Chapter 6, we talk about how to set memory, how to actually set simple memory circuits, not big, massive memory circuits. We wait until chapter 11 to set big, massive memory circuits. But in chapter 6, we talk about the simplicity of simple memory circuits, and that's it. We wait and talk about more sophisticated ones later. Right? But chapter 5 is just combinational circuits is all it is. Combinational circuits. Okay. So this is what we talk about, and this is one of the things that they identified from the Germans, how to do a project, and so what part are you involved in? All of them. All these parts you are actively involved in, okay? Now, some of you will work in a plant or in a facility where you are assigned a specific area, and that's all you work at. I really appreciated working for Owens Corning Fiberglass. I work for two basic companies, Libby Owens Ford and Owens Corning Fiberglass, and I appreciated them both, but I especially appreciated Owens Corning because why? They had you active in all phases. You worked through every phase, including the startup, but you paid your own dues. In other words, if you made a mistake, you ended up fixing it, usually. Now, that doesn't mean that you didn't have projects that got passed from individual to individual. One person might be moving, and they would pass that project on to somebody else. But it was expected that somebody in the group would do each project all the way through. Many times at the end of a project, when it got really hot and really involved, the startups, there would be people that would come on with you to help you to get started up. In other words, you might be responsible for starting up an area, and you might have 2 or 3 more people that come in and help you in the heat of that project to start it up. Most of the time, the programs were written by you. In other words, you didn't have somebody sitting back in another area that was writing a bunch of programs that then you had to start up. You wrote the program, you started your own programs, and I like that. That was very, to me, that was the way to do it, and I appreciated that. Now, that's what this is about, this setting up and going through a project from start to finish, from the first idea, from the initial idea, all the way through the commissioning and the documentation. I hated doing reports. I did them, but I hated them at the end. I always hated finishing things up. I languished for days on that, but anyway, the service part. And if you ask me to physically write production reports, I would go nuts, because the people that are asking you to do this are many times people that want to hold on to you for as long as they can. And so they say, well, will you move that period over by one space or whatever? And you say, why are you making me do this? And I'll just stop with that. I hate reports. Hate doing reports out of production reports, okay? I hated that. But again, that was me. So basically, we'll start with chapter 5, finish chapter 5, and we'll move on. I'll have your stuff. If you still have the quiz not done, get it to me tonight, or get it to me now, and then we'll call it quits. Take care. Have a good day.